Okay, I'm going to go through the FRQs as part of the Unit 1 practice test. So the first part over here, we're saying iron metal reacts with concentrated nitric acid to form NO and Fe3+. Now this is very much like the lab that we did where we had copper reacting with nitric acid, or like the demo we did where nitric acid acts on copper. So the first thing is write the balanced oxidation half reaction. So who's getting oxidized? We have iron metal, and that is turning into iron ions. Okay, so that is our oxidation half reaction. So Fe turns into Fe3+. This side is more positive by 3, so we add 3 electrons, and there's our balanced half reaction. Okay, for the reduction half reaction, well, we have the nitric acid, HNO3, and that's going to turn into NO. So we could start with that, or we could say, okay, we know this is a strong acid, so let's think of this as H plus and NO3 minus, and turning into NO. So we can do it either way. We should get the same answer either way. So what happens on this is we have the nitrate and the NO. So we have 3 O's, we have 1 O, so we have to add 2 waters to get the 2 extra O's. Now that gives us 4 H's. We have 4 H pluses. Or if we were doing it this way, we would have HNO3 and we'd have to add 3 H pluses. And we can see what we have. We have 4 pluses, we have 1 minus, so that's a 3 plus on this side, neutral on this side. This side is more positive by 3, so we add the 3 electrons. Now what's convenient about this, we have to combine these two equations, and the 3 electrons just cancel out, so that's nice. So we just copy everything down. So the iron plus the hydrogen ions plus the nitrate, okay, turn into iron ion and NO and 2 waters, and that's our balanced overall equation. Now again, later on we're going to see the value N, okay, and that's the number of moles of electrons that get transferred, and so that's going to be 3 because we canceled out the 3. We don't need that now, but we are going to see that eventually. So letter D says, what's the minimum value of concentrated nitric acid needed to dissolve the 3.25 gram iron nail? Okay, well this is our, just a line equation like we did the lab. So we have grams of iron. Okay, we have to go grams of iron to moles of iron. That's molar mass of iron. And then this is the kind of slightly tricky part, and that is the idea that, it seems reasonable that if we're saying for every iron we need 1 nitrate, so we're going to need 1 HNO3, but in fact, we actually need those 4 H pluses, because this is a reaction where, it's not that we have a lot of water around there. This is the concentrated nitric acid, and so the H pluses actually are going to be coming from the acid, and so we're going to need 4 HNO3s. They're going to give us 1 nitrate that changes into an NO2, but we need those 4 H pluses here in order to form these waters. Okay, so when we put this together, we're going to need iron and we're going to need 4 H pluses. So that's where we get this 1:4 ratio. Then after we have moles of HNO3, we're going to use the molarity as a conversion factor, 15.8 moles per liter. And so we come up with 0.0147 liters. Now, if we were doing this in class, we would move that decimal point over and say, okay, we're going to need 14.7 milliliters, because that's what we're going to measure out. Now, when we get to part E, okay, the reaction mixture now is placed in a 100 milliliter volumetric flask, just like we did in the lab, and distilled water is added up to that etched line. So what's the concentration of the resulting solution? Now, this is a pretty vague statement, okay, what's the concentration in terms of what? And what I really meant, I should have said Fe, what's the concentration of Fe3+, because we're about to do a titration, and that titration we're talking about, if I have this much iron, how much sulfide am I going to need? So I'm really interested in the iron concentration, and if we put this on another test, we're going to make it more clear and say Fe3+. So I have this many grams of Fe, okay, and all those Fe's turn into Fe3 pluses. So I can use my grams, go my grams to moles, the iron, okay, and every one of those irons turns into an Fe3 plus. And then I want to divide this much of it is going to give me my moles of iron. Divide by the total volume, 100 milliliters, 0.1 liters. So we get a concentration of 0.582 molar Fe3+. And the last part here, do a titration. And we're going to use sulfite that turns into sulfate to react with our iron 3+ that turns into iron neutral. So sulfite is a reducing agent. It'll reduce our iron ion into iron metal. So what do we have? We have 10 milliliter sample of our iron, okay, the solution made back here. So 10 milliliters. You use our molarity as a conversion factor, 0.582 moles per liter, or per 1,000 milliliters. Then we use the ratio in the formula, in the equation. So for every 2 moles of iron, we need 3 moles of sulfite. And then the concentration of the sulfite, okay, is 0.1 molar sulfite per 1,000 milliliters. Okay, and that is given right here. Potassium sulfite is just our sulfite. So we use molarity as a conversion factor again. So molarity, and this is the mole ratio from the balanced equation. And we get all done, we find out they have 87.3 milliliters. Now notice it would be improper to try to use volume times molarity equals volume times molarity, okay, because that really is a dilution formula, and it, mistakenly some people try to use that in a titration. We should really do it this way here with the line equation. Okay, next problem 22, we say a student is practicing writing equations and drawing particulate diagrams of reactions. So if we have equal volumes of equal molar solutions of hydrochloric acid and sodium hydroxide, so equal volumes of equal molar solutions, that means we have 1 HCl for every 1 sodium hydroxide. And that's the idea of what's going on. So what's going to happen is going to be double replacement. We're going to get water, and we're going to get sodium chloride. And the question is, write the balanced molecular and net ionic equation. So we don't have the molecular. Here's my molecular equation up here. It's a little sloppy, but that's right there. Okay, including states. So this is aqueous, and this is aqueous, okay, because those are solutions. H2O is a liquid, and NaCl is aqueous, because sodium compounds are soluble. Then what's going to happen is the Cl's are going to be spectators, the Nas are going to be spectators, NaCl is going to cross out. So here's our net, and our net is H plus OH minus turns into water, and that is our entire balanced net ionic equation. Now the student draws the following diagrams representing each reactant. So this is supposed to be HCl aqueous, and this is supposed to be a picture of NaOH aqueous. Okay, and then when you get done, we're going to have NaCl, and we're not drawing the waters. So what mistake has the student made? Well, the mistake is HCl is a strong acid, so each one of these should be split up into ions. Strong acids dissociate 100%. Now this would have been good if we had something like HF, which is a weak acid, but for HCl, everybody should be ions, should be 100% ionized. Okay, so the answer is, since HCl is a strong acid, it should be 100% dissociated. Okay, no HCl molecules remain in solution. C, equal volumes of equal molar solutions of hydrochloric and sodium bicarbonate are mixed. Write the balanced molecular and net ionic equation. So again, we're missing our molecular. Let's put it in. I'm going to put it in way down here. So if we had HCl, and that's aqueous, okay, plus H2CO3, okay, and that's going to be, I'm sorry, that's wrong, a sodium bicarbonate, so that's NaHCO3, and that's aqueous. That's going to turn into Na and Cl, and that's going to be aqueous, and H and HCO3, that's going to be H2O, which is a liquid, and CO2, which is a gas. So the idea here is that we're going to form H2CO3, which we know decomposes into H2O and CO2, because we memorized that. Okay, so this is our balanced equation for the molecular. Now, this is a soluble compound, so that's going to break up into ions. This guy is totally, strong acid is going to break up. This guy is going to break up. So we're going to have H plus HCO3 minus turns into H2O and CO2. So this is the perfect net equation for this. Now, the student states that the third picture in B above also represents the final solution for the reaction in C. So in our final reaction in C, the idea is, okay, we're going to have, sodium ions, we're going to have chloride ions, water, which we're not drawing, but the CO2 gas is going to escape. So I would say, yes, I agree that this is the right picture for the reaction with bicarbonate because all the CO2 has, left the reaction. So all that's left in solution is sodiums and chlorides and waters that are not drawn. So I would say, yes, this is going to be that. This is I agree that that picture works for both reactions. Now, you could also disagree, and if you disagree and say, well, CO2 does dissolve in water a little bit. So in here, you're not going to have CO2s, but you might have bicarbonate ions. Okay, you might have a little bit of carbonic acid. Okay, that will be in the solution as well. And if that's what you're saying, yes, I agree that this probably would have carbonate bicarbonate. And just if we bubble some CO2 through a saltwater solution, we would get a little bit of bicarbonate or a little bit of carbonic acid in there. Not much, but it would be some noticeable. Okay, and so we would take either agree or disagree. It really depends on your discussion. And that's the FRQ.